Ch9I. The first one is about mathematical induction. Mathematical induction first appeared in one of Pascal's properties discovered from the arithmetic triangle. So now we can look at example how to use mathematical induction to prove a formula involving n. This example is on page 462. So we want to prove the formula 1 cubed plus 2 cubed plus 3 cubed plus ... plus n cubed equals n squared times n plus 1 squared over 4. If you had taken 306 or if you had taken calculus B, you may have already seen this formula, or you already know how to prove this formula using mathematical induction. The basic idea is two steps. First step, we want to prove this formula holds for a particular number, for example, for n equals to 1. And then we want to prove if this formula is true for k, then we can prove the formula is also true for k plus 1. And the reason we have to use mathematical induction is that the formula involves n, and n can be anything. So in this case, this single formula here actually describes infinite many formulas. For example, because n is a variable, n can change. N can change from 1 to infinity, any number. So if n is 1, what is the left side? The left side is simply 1 cubed, because the pattern on the left side is the base goes from 1 to n. If n is 1, which means the left side, the base goes from 1 to 1, which means we only have one term. And the right side, if we look at the right side has only one single term, so it's just simple algebra, which we just replace n with 1. And we can simplify this to get 1 squared is 1, 2 squared is 4, divided by 4 is 1. You can see the left side is the answer is 1 after we simplify it, and the right side is also 1. That means the left side equals the right side. But n can be 2, or n can also be 3 or 4. Keep going, any number, 100, 10,000, a million. So when n changes, we get many different formulas. So I can look at, for example, if n is 2, the left side goes from base 1, always starts with base 1 in this formula, and to base 2. So every time the base is 1, and it stops at n, which in this case, second case, n stops at 2. So the left side, if I simplify it, I get 1 cubed is 1 plus 2 cubed is 8, so I get 9. And the right-hand side, it's a single term. It's not like the left side, it has many terms, n terms. So if n is 1, I only have 1 term. N is 2, I have 2 terms. If n is 3, I will have 3 terms. On the right side, it does not have the dots, so we only have 1 single term. So let's say n is 2, I replace n with 2. And I simplify it. 2 squared is 4. 2 plus 1, 3 squared is 9. Divided by 4. I cancel 4, I get 9. You can see the left side is also equal to right side. And of course, we can verify 3 or 4, but since we have infinite many integer whole numbers or natural numbers, we cannot verify every single formula for every single n. So, but we need to prove this formula holds for every single n. How do we do that if we cannot make a list of all of them? So this is the idea of mathematical induction. So when we do the proof, we cannot use all of this. Here I'm writing down some of the examples, some of the ends to help you to understand what this formula actually is. But when we do the proof, because we cannot, this is not practical, because we cannot make a list of all the integers for n. We can only do a few of them. For example, I did 1, 2, and we can do 3 and 4 and 5, but we cannot do all of them. So that's why we have to use mathematical induction to prove this. So step 1 is very easy. Just do one of them. So a particular one. Usually we pick the very bottom one. So for example, n starts from 1, so I let n equal 1. And I checked both sides. I checked both sides like I did. So the left side is 1 cubed, because when n is 1, we have to, it's kind of difficult to determine the left side for some of the problems. So we have to follow the pattern. The pattern is, in this formula, is cube power of natural numbers from 1 to n. So if n equals 1, that means the cube power of integers from 1 to 1. If it's from integers from 1 to 1, which means we only have a single term. So that's why we have 1 cubed equals 1. And the right side is very easy, just replace n with 1. So I get L equals 1. So step 1, we only proved that this formula holds if n equals 1. How do we prove the formula holds for n equal to 2, n equal to 3, n equal to 4, and so on? We don't need to do all of them. What we need to do is, this is a very important step, we assume the formula holds for n equal to k. K also can change. And we want to prove the formula also works for n equal to k plus 1. So let's try to, if we assume that formula holds for n equal to k, what is the formula? So that means we need to replace n with k. Okay, again, the left side follows the pattern. The base goes from 1 to n. What in this step, second step, because n is k, so which means n, the base goes from 1 to k. So 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus k cubed. So the last term we stop at k. And the right side is easy, single term, so we just replace n with k, because we assume n equals k. Okay, and we also assume the formula is correct for n equal to k. That means we replace n with k. Now our goal is to show that the formula also is correct for n equals k plus 1. And this is something we want to prove. So this formula is our assumption. We don't need to prove it anything. But the goal is what we want to prove. Okay, so first, if we want to prove the formula is correct for n equal to k plus 1, we have to know what formula looks like if n equals k plus 1. So let's write down the formula. The left side, again, goes cube power of integers from 1 to n. What's n? In this case, it's k plus 1. So we're going to stop at plus k cubed plus k plus 1 cubed. So the reason I want to write down the previous term of k plus 1 is we can compare the assumption and our goal formula. And the right side, again, it's easy, just replace n with k plus 1. So the right side, replace every n with k plus 1. So the first part, I replace n with k plus 1 here, and also replace this n with the k plus 1. So k plus 1 plus 1. And so this is the formula I want to prove. Or I can combine k plus 1 plus 1 and get a k plus 2 squared. So this is the formula I want to prove. And how do we prove this formula? Don't forget we have assumption here. The assumption means this is already, we assume this is true, so I can use this. If we compare these two formulas, the assumption formula and the goal formula, the left side is very close. The left side, the assumption formula goes from 1 to k cubed, 1 cubed to k cubed, and the goal formula has an extra term which is k plus 1 cubed. So if we combine them, there's only one extra. So if I want to get my goal, I can add this extra term, k plus 1 cubed, to both sides of the assumption formula. And what did we get? If I add both sides, so I copy the left side of original formula. That's the original formula on the left side of the assumption formula. I add an extra term, k plus 1 cubed. So this is the one I add. And the right side I also copy it. And then I also have to add, because I add the same thing to both sides. That won't change the equation, the balance of the equation. So this is what I add both sides. You can see, if I subtract that k plus 1 cubed from both sides, I go back to my assumption. But I want to keep this. Why? Because this is what I want, the goal. So the left side is exactly what I want in the goal formula. And so the only thing left is to prove the right side is also the same as the one in the goal formula. They look a little bit different, but if we use algebra to simplify the right side, we should be able to get this here. So the left side, I don't do anything. I copy it, 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus k cubed plus k plus 1 cubed. And the right side, I add these two terms. And because one of these fractions, I need to equal a denominator. The common denominator is 4, so I equal the denominator of the second one, multiply 4, both top and bottom. So I can put k plus 1 cubed over 1 and multiply 4, both top and bottom. And now I can add, because I got a common denominator 4, I can add the numerators. So k squared plus k plus 1 squared plus 4 times k plus 1 cubed. And still, if we compare the right side, the denominator is 4 and the top still a little bit different. How do I get that? If we notice that factoring out k plus 1 squared, we can get what we want. So what I'm going to do next is to notice both terms contain k plus 1 squared, 2 copies of k plus 1, and this one actually has 3 copies of k plus 1, but we can only pull out k plus 1 squared at most. So I pull out k plus 1 squared, and what's left in the first term, k squared. I'm out of this, I'm going to put it right here. So k squared plus, and the second term, in the second term, if we pull out k plus 1 squared, we still have a 4 left and 1 copy of k plus 1. And if we factor k squared plus 4k plus 4, which is exactly k plus 2 squared, so we get what we want. So I'm a little bit out of space, so the next step, if we write it down, is exactly the goal formula. So that's how we use mathematical induction to prove. The homework actually should be easier than this one because it doesn't have a Q power. So to follow the steps here, step 1, we need to prove the formula is true for n equal to 1, which is very easy. Check both sides, left and right. Step 2, we assume the formula holds for n equal to k, and we prove the formula actually can be extended to k plus 1. And if we think about it, looks like we only proved the 2 things. It doesn't look like the formula holds for every single n, because there are infinite many single n. But if we look at step 2, it already includes every single n, because we assumed if the formula is true for k, then the formula is also true for k plus 1. And then k can change. So if k is 1, And if the formula holds for 1, then formula holds for 2. If the formula holds for 2, then formula holds for 3, because if k is 2, then we can get 3. If the k is 3, I can get a 4. If k is 4, I can get a 5. So this can continue because k can change. So the only question is the formula true for 1? Yes, because we already proved in step 1. So combining these two steps, we can prove the formula holds for every single n, because 1 implies 2, 2 implies 3, 3 implies 4, and so on. The second homework question is about probability.